So advanced radiation. By the way, we have another tutorial next week. I think it's going to be our last one. It's the end. I'm not sure. I'll try and do a revision one the week after, but there's no guarantees. Okay. So if you guys go and ask Chris and bug him, then I'm sure he'll let me do another one if you guys want. Okay. Yes. So yeah, you guys can ask Chris if you want it. So radiation advanced. So we have an X-ray tube. Electrons are accelerated to 40 keV. So that's kilo electron volts. Okay. So it's like I said before, it's confusing because you might think it's kilovolts. So don't do that. If it's got an E in it, that's electron volts. Okay. So the energy of these electrons is equal to 40 kilo, which is 40,000. So 40 times 10 to the 3 electron volts. Okay. And we want to find the shortest wavelength possible for the X-rays that are emitted. Okay, so so the thing that you have to assume here or kind of understand is the fact that in an X-ray tube, so for X-rays, the energy of electrons will be equal to the maximum energy of the X-rays that come out, okay, or the photons that come out, because X-rays are just photons that have frequency in that X-ray range, okay, so X-rays or photons, okay. So our photons, the energy of our photons will also be 40 times 10 to the power of 3 electron volts. Okay, and so we need to convert, we can convert that later. We want to find the wavelength of these photons, and remember, if you know the energy of the photons, you can calculate the wavelength, the frequency, and the momentum. So we just want to calculate the wavelength. So that's the wavelength and the minimum wavelength. So that's going to be Hc divided by the energy. Okay, so H is our Planck's constant, 6.63 times 10 to the negative 34 times C, which is the speed of light in vacuum, divided by our energy. So that's 40 times 10 to the power of 3, and then we need to convert that into joules, so we're going to times it by 1.6 times 10 to the negative 19. Okay, so that's our energy in joules. And that will give you 3.1 times 10 to the negative 11 meters. Number 2, an alpha particle is accelerated from rest through a potential difference of 500 volts. What is its final speed in meters per second? And the mass of an alpha particle is 6.6 times 10 to the negative 27 kilograms. So I'm sure you all still remember what an alpha particle is. So it's just 2 protons and 2 neutrons. Okay, so we need to know the charge of an alpha particle. The charge on an alpha particle is going to be 3.2 times 10 to the negative 19 coulombs, which is just the charge of 2 protons. So our kinetic energy is equal to the electrical potential energy, which is equal to Q times V. So our charge multiplied by the voltage. And then so kinetic energy is equal to half mv squared. Right, so then you can just rearrange this for the velocity, which is what we want. So on my cheat sheet I have it pre-rearranged because this is quite a common question. So the velocity, so this is small v, not uppercase, so this is lowercase v for velocity. Velocity is equal to the square root of 2 times q, our charge, multiplied by big V, which is the voltage, divided by the mass. Okay, so 2 times our charge, which is 3.2 times 10 to the negative 19. Our voltage is 500. And our our mass is 6.6 times 10 to the negative 27. And that will give you 220,000, which is 2.2 times 10 to the power of 5 meters per second. Oops. So on my cheat sheet I have it rearranged like this. Number 3, so waves have particle-like properties. What's the momentum of each photon with a frequency of 7.5 times 10 to the power 14 hertz? Okay, so the momentum of a photon is equal to h, the Planck's constant, multiplied by the frequency, divided by c, the speed of light. So that's 6.63 times 10 to the negative 34 times our frequency, which is 7.5 times 10 to the power 14. And our speed of light is 3 times 10 to the power of 8. And that will be 1.7 times 10 to the negative 27 kg meters per second. Okay, that one was pretty easy. Now we're back to binding energy. Okay, so number 4, the atomic mass of potassium 40 is 39.964 atomic mass units. What's the binding energy per nucleon of potassium 40 in mega electron volts? Okay, so you've been given the mass of a proton, the mass of a neutron, and the mass of an electron. Okay, so first of all we need to figure out how many protons, neutrons, and electrons we have. So if it's 40, 19, 40 and 19, that means that we have 19 protons. We have, how many neutrons are we going to have? Yep, 21. 21 neutrons. So that would be, that's 40 minus 19. So, and then the number of electrons is going to be the same as the number of protons, because it's going to be electrically neutral, because it's an atom. Okay. So we need to figure out the unbound mass. Oops. So the unbound mass of these, so that's going to equal 19, so we'll do the protons first, 19 times the mass of a proton, which is 1.00728, plus the neutrons, which is 21 neutrons, times the mass of a neutron, which is 1.00867, plus 19 electrons, so 19 times 5.4858 times 10 to the negative 4. Okay. So when you put it in your calculator, you don't have to put brackets around these ones, because it's going to do the times first, which is what you want. And that's going to be 40.3308 atomic mass units. Okay. And just pay attention to the units, because although most of the time it will be in atomic mass units, you can never be sure. Yeah, it probably will be in atomic mass units, but just make sure you check. Okay, so 40, so that's obviously more than the atomic mass, which is 39.964. Okay, so the difference in mass is going to be 40.3308 minus the atomic mass, which is 39.964, and that's equal to 0.36681 atomic mass units. Okay, so our binding energy is equal to the atomic mass units, so 0.3681 times, so we want to turn that into mega electron volts, so 931.5, and that will be 341.5 mega electron volts. So that's the total binding energy, but that's not what we want here. We want the binding energy per nucleon. So we have 40 nucleons, so we have to divide that total binding energy by 40. Okay, so we're going to divide that by 40, which will equal 8.54 mega electron volts. Okay, so that's going to be option D. All right. So I'm not going to go through the next one, number 5, because that's exactly the same as the question number 4. Okay, so you guys can try it on your own, see if you get the right answer. Sorry?
What is the answer?
It's D. Yeah. So you should get D, and if you get stuck, you can look at my working on that I'll post up later on. Okay. Number 6, the single electron in a hydrogen atom is initially in the ground state. Okay, so here's our nucleus. All right, and we have our ground state atomic energy level, or the orbital. We have the second energy level. We have the third energy level / orbital. Okay, so this is n equals 1, n equals 2, n equals 3. So our electron starts off in the ground state, so n is equal to 1, initial n, Ni is equal to 1, and then it absorbs a photon, so a photon comes in, and it hits this electron, there's a photon, it hits that electron, the electron absorbs that photon, so it's going to gain energy, and it goes up into the third orbital. Okay. So now what's the wavelength of the photon that's absorbed by the atom? So first we need to find out the energy of the photon. So that these two orbitals, the change in orbital level is going to correspond to a change in energy, and that change in energy is going to be equal to the energy of the photon. Okay, so we need to find out what delta E is. So the equation for that is delta E is equal to Z. So Z is the number of protons in the nucleus, and that's going to affect the energy, the difference in energy between the orbitals. And so bracket final orbital to the power of -2 minus the initial orbital to the power of -2 times 13.6 times eV, or electron volts. Okay, so that's quite similar. So remember in our last tutorial we did Z is equal to the square root of delta E, so that's just rearranged from this equation. Okay. So we have a hydrogen atom, so a hydrogen atom is just going to have one proton. So Z is going to be equal to 1. So 1 squared is just 1, so you don't have to put that in there. And then the final energy level is 3. So 3 to the power of -2 minus our initial energy level, which was 1. So 1 to the power of -2 times 13.6 times, we want our energy to be in joules, so we have to convert it into joules by multiplying it by 1.6 times 10 to the -19. And that will give you so it'll be a negative number, 1.9342 times 10 to the -18 joules. Okay, so that's our difference in energy, and that's going to be equal to the energy of the photon that was absorbed. Now, if we know the energy of the photon, we can figure out the wavelength. So the wavelength is going to be equal to H times C over the energy. So H is 6.63 times 10 to the -34 times our speed of light, which is 3 times 10 to the 8, over our energy, which is, so we don't have to worry about the negative sign, 1.9342 times 10 to the -18. And that's going to be 1.03 times 10 to the -7, and that will be in meters. Okay, and you want to turn that into nanometers, so divide that by 10 to the -9, and that will give you 103 nanometers. All right. Next so this is again pretty similar. So we have a hydrogen atom. It only has a single electron. It goes from the 5th energy level down to the 2nd energy level, and it emits a photon. Okay, so I'm just going to go through it quickly because it's exactly the same as the last one. The change in energy between the two orbitals is going to be equal to Z squared times the final orbital level to the power of -2 minus initial orbital to the -2 times 13.6 times EV. So if it's a hydrogen atom, it has 1 proton, so that's 1 squared. And the final energy level is 2. So 2 to the power of -2 minus our initial, which was 5. So 5 to the power of -2 times 13.6 times 1.6 times 10 to the -19. So we're turning that into joules. That will give you 4.5696 times 10 to the -19 joules. And then again, the wavelength is equal to hc over the energy. So that's 6.63 times 10 to the -34 times 3 times 10 to the 8 divided by our energy, which is 4.5696 times 10 to the -19. And that will be 4.35 times 10 to the -7 meters, and you want to turn that into nanometers, so divide by 10 to the -9, and that will give you 435 nanometers. Okay. Number 8, we have a decay equation. So we want to find out the unknown particle, which has been given the symbol X. Okay, so I'm going to quickly explain beta positive and beta plus and beta minus decay. Okay, so I'll start off with beta plus decay. So in beta plus decay, you have a proton. A proton resides in the nucleus, right? So a proton is in the nucleus. It turns into a neutron. So the proton turns into a neutron, and since a proton is positive and a neutron is neutral, it means that it has to lose a positive charge. And if it's losing a positive charge, it's going to get rid of a positron. Okay, and that positron is going to be emitted, and it's also going to emit a neutrino. Okay, so the symbol for positron is beta plus, and the symbol for a neutrino is V, or V subscript E. Okay, and so if you're losing a proton and it's turning into a neutron, the number of nucleons isn't going to change, right? Because it's just going from a proton to a neutron. So the number of nucleons, which is your which is your mass number here, A, isn't going to change, so it's going to remain exactly the same. But Z, you're losing a proton, so it's going to be Z minus 1. So Z minus 1. And if you have a change in the number of protons, it is now a new atom. Okay, so it's going to be a different element. Okay. All right, so you're going to have a beta positive particle and a neutrino. Okay, so that's beta plus decay. So yeah, number 8 should be option C, a positron. Now number 9, we have, so this is going to be beta minus decay. So in beta minus decay, we have a neutron. So this was beta positive, beta plus decay. Now we have beta minus decay. Beta minus decay. So if I asked you what the opposite of an electron was, I think most of you would probably say a proton, but it's actually a positron. Okay, so the opposite of a proton, the opposite of an electron is a positron. And I don't know if you noticed when you did the binding energy problems, but you'll see if you look at the mass of a proton, it's 1 atomic mass unit. If you look at the mass of a neutron, it's 1 atomic mass unit. But if you look at the mass of an electron, it's much, much smaller. So it's 0.000549 atomic mass units. Okay, so a proton and neutron is actually made up of positrons and electrons. Okay, so protons and neutrons can actually turn into, can actually switch between being protons and neutrons by getting rid of either a positron or an electron. Okay, so in this case, in beta minus decay, we have a neutron which says, I'm sick of being a neutron, I'm going to turn into a proton. So it's like going to kick out an electron. And so if it kicks out, if it loses an electron, it's going to be net positive. Okay, so it's now a proton. And it's also got to emit an anti-neutrino. So the symbol for an electron is beta minus. Okay, so if you see beta minus, that's just an electron. And the symbol for the anti-neutrino is a V, but with that macron, that line on top. Okay. So I just remember it by, you can just write it down, or you can remember it by going, the minus will just go on top of the V. Yeah, and so then, again, you're not going to have any change in the number of nucleons because you're just turning a neutron into a proton. So the number of, the mass number, A, will remain the same. But the number of protons is now going to increase. So it's Z plus 1. Okay, and if there's a change in the number of protons, it's a new element. So that symbol is also going to change. So that's going to be plus a beta minus particle and an anti-neutrino. All right. So if they ask you about decay questions, you're just going to look at, first of all, you're going to look at the atomic number, see if that changes. If it changes, it's probably going to decrease by 4, and that's going to be alpha decay. If that doesn't change, then look at whether the atomic number changes. So if it decreases by 1, so if it's minus 1, then it's beta plus. If it's plus 1, then it's beta minus decay. So that's like the opposite, right? Yep. So we'll go on to the next page. We've just got 2 more questions on beta decay. Number 10, we have a sample of aluminium, which has 25 nucleons and 13 protons. So, and it's decaying and it's emitting positrons, so that's beta plus decay. Okay, and which of the following is a possible daughter nuclide? So, the number of nucleons, so beta plus, I'll just write this down. So it's going to be A, Z, X, turning into A is the same, and then if it's beta plus, it's going to be beta, Z minus 1. Okay, so the atomic number, the mass number has to be the same, so that still has to be 25. The atomic number is going to be minus 1, so 13 minus 1 is 12. And then you're just going to look for the one that has 25 and 12. That's going to be option C, okay, which is magnesium. Okay, so pretty simple. Last one. We have which one of the following is the correct decay scheme for the production of beta plus radiation from the decay of potassium 40? So we have beta plus decay. So we should have the same number of nucleons, 1 less proton, and we'll expect a new atom, a different symbol, will be emitting a positron, and you'd also have to be producing a neutrino. Okay, so this is a neutrino. All right, so on my cheat sheet I have this written down. So it's going to go from 40, 19K into 40, 18. Okay, so if you look at option B there, it's also got 40 and 18, and it's got beta plus and a neutrino, but that's incorrect because you've changed the number of protons, so it can't still be a potassium atom, right? So it has to change into something different. So it's going to be option D. So it's going to turn into argon. Okay? Sweet as. Thanks, everyone. I'll see you next week.
So you're not covering the other like all this other stuff?
I'll